Assalamualaikum and a very good afternoon, everyone. Thank you. I hope you are well. For those who have not scanned the QR attendance, you can just leave your metric number in the chat box. I will manually key in the attendance later. All right. Have you completed all the activities, class activities for learning unit 2?
Yes, doctor.
Yes.
Yes.
I hope everyone is okay with all the calculations. If you find you have difficulties, you can always ask in the WhatsApp group, or you can email me. We will try to discuss how to get the answer. But of course, I cannot give you the whole steps for doing it. The calculation steps, but I can tell you, I can give you hints on how you can solve the problems. All right. Okay. Today, we will start learning unit 3, which is on the gravimetric analysis. Okay. Before we discuss further on gravimetric analysis, I would like to share with you the learning objectives for this learning unit. So at the end of this learning unit, you should be able to first describe precipitation gravimetry, explain the steps involved in precipitation gravimetry, identify the different types of gravimetric analysis, solve problems associated with gravimetric analysis. And today, in this lecture, I'm going to cover the first part, the first 3 learning objectives, which is to describe, to explain steps involved, to identify different types of gravimetric analysis. And then in our next lecture, which is next week, we will try to solve problems associated with gravimetric analysis. Okay. Whether you realize it or not, you have already actually done experiment on gravimetric analysis. Okay, so when you conducted experiment 2, you have learned from the procedure that in order to get the suspended solid reading, total solid reading, and dissolved solid reading from the water sample, in water sample analysis, you have to find the mass of the solid. Okay, so what we have here is a simple gravimetric analysis which enables you to have an information on the analyte that you want to look for, which is in this case suspended solid, total solid, and also the dissolved solid. Okay, that one is one simple gravimetric analysis. After this slide, I will ask you which one of these 3 gravimetric analysis type was involved in experiment 2. Okay, so what is gravimetric analysis? Gravimetric analysis is an analytical method based on measurement of mass of an analyte, okay, or a compound containing the analyte. Okay, so anything which is related to the determination of mass of an analyte is called gravimetric analysis. So it comes from the word gravity. Gravity is related to weight, and weight is also called mass. Okay, so that's why it's called gravimetric analysis. It involves the determination of mass of your analyte or compound containing your analyte, which can be calculated later to gain the information on the mass of your analyte. Okay, so there are 3 types of gravimetric analysis that will be covered in this learning unit, although we actually have more than these three types of gravimetric analysis, but we will cover only those three. Okay, basically we have precipitation gravimetry, volatilization gravimetry, and particulate gravimetry. What is precipitation gravimetry? Precipitation gravimetry is about the determination of the mass of a precipitate. So we will learn after this what are the steps and the factors involved in precipitation gravimetry and when it is used. Okay, so precipitation gravimetry involve the determination of mass of a precipitate. Okay, and then volatilization gravimetry is signaled by the loss of a volatile species. For example, you use heat to lose weight or to lose the mass of your sample, and the volatiles coming out of your sample during the heating process is called the volatile species. And the loss of the volatile species is the signal of we are having volatilization gravimetry. So in short, volatilization gravimetry normally involves heating or releasing the volatile species in our compound. Okay, this is in order to get information on the mass of volatile species of our analyte or compound containing our analyte. Okay, and the third one that we are going to cover in this learning unit is the particulate gravimetry. It is about the mass of a particulate analyte determined following its separation from its metric. For example, you have a solution where you can separate the particles in the solution from the solution using filtration process. Okay, so you deal with the particles of the solution. Okay, so that's called particulate gravimetry. So when you look at these three types of gravimetric analysis, which one do you think was involved in experiment 2? Can you type in the chat box? Which one do you think? Is it precipitation gravimetry, or volatilization gravimetry, or particulate gravimetry? Does it involve precipitation process? Okay, some of you answer precipitation gravimetry. Any other answer? Some of you mentioned volatilization gravimetry, precipitation gravimetry. Most of you answers precipitation gravimetry. All right. Okay. We'll look after this. What is meant by precipitation gravimetry? Precipitation gravimetry involves the addition of precipitation reagent. Okay, meaning to say you have your analyte A, you add precipitation reagent R to produce precipitate AR. Okay, does it involve any precipitation reagent in experiment 2? Yes or no? Was there any precipitation reagent in experiment 2? Norain said no. What about others? Alicia said no. Teresa said no. Yes. There was no involvement of precipitation reagent in experiment 2. So what could it be? Is it volatilization gravimetry or particulate gravimetry? All right. When we are dealing with volatilization gravimetry, as has been mentioned previously, it's about heating the sample or any treatment which cause the sample to release volatiles. Okay, in our case, in experiment 2, what we release during the drying of sample is only moisture, because we dry the sample at a temperature of 100 to 120 degrees Celsius only. At that point of temperature, the only thing that come out of the sample is only the water or moisture. Okay, so we don't call it volatilization gravimetry, we call it particulate gravimetry for experiment 2. Okay, all right. Now we go back to the precipitation gravimetry. Okay. In precipitation gravimetry, it always involves the analyte and precipitation reagent to produce precipitates. Okay, and that's why it's called precipitation gravimetry, because the end product that we have in this analysis is the precipitate. Okay, so small a is the number of moles of analyte A. Small r is the number of moles for reagent R. AR is a pure insoluble precipitate. So the characteristic of the precipitate is it must be pure and it must be in insoluble form, meaning to say that you cannot dissolve it. Okay, it is in the form of solid, which we can dry, weigh, or ignite to convert to something that we can weigh. Remember, the purpose of gravimetric analysis is to have the end product in the form of mass determination. Okay, meaning to say that you have your end product, you can weigh your product, you can get the mass of your product, and from that product, the mass of that product, you can calculate the amount of analyte in your product or in your sample. Okay. All right. Before we go further, I would like to stop sharing the slide, and instead I would like to share with you the YouTube video on gravimetric analysis. Can you see the YouTube video?
Yes, Doctor.
Okay.
At the end of this video, you should understand the principles of gravimetric analysis and be able to perform calculations relating to gravimetric analysis. Let's start with a definition. Gravimetric analysis is an analysis method based on mass. While there are several different types of gravimetric analysis, the precipitation method is the most common and the one that we'll be using in this class. In the precipitation method, an unknown is isolated by precipitation and filtration. We then take the solid product that we filtered out of solution, dry it, and take its mass. You might recall in previous labs that we've used the term heat to constant mass. This is a technique to ensure that all the water has been removed from the sample. Heating to constant mass involves heating the sample, weighing it, then heating again and weighing again until the mass stops changing. When the mass stops changing, we know that all the water has been evaporated from the sample and all we're left is pure sample. Here's a schematic showing us a particular example of gravimetric analysis. In this example, we're attempting to precipitate out all of the lead-2+ ions in solution. First, we take a sample containing lead-2+ ions and some other chemical species and dissolve it in water. Once it's dissolved, we add another aqueous solution that contains an ion which will form precipitate with the lead-2+ ion. In this case, that ion is sulfate. The sulfate combines with the lead 2 plus to form solid lead 2 sulfate. This solid can be easily filtered out, dried, and weighed. The mass of this solid can then be used to determine the amount of lead 2 plus in the original sample.
Right. Now, if we look at the diagram showing the gravimetric analysis, which is the precipitation gravimetric analysis, you can see here the first thing you have in this analysis is a solid compound which contains your analyte and other species and other chemical species. For example, in this case, let's say your analyte is Pb2+, okay, lead 2+. It's denoted in orange in color, and other chemical species is yellow in color. So we cannot separate Pb2+ from other chemical species in its normal form, in its solid form. Why? Because they are chemically bound. Okay, so what we do is, first, we need to dissolve the solid, meaning to say we need to prepare the solution. We need to prepare the Pb salt solution. Okay, so after we prepare the Pb salt solution, the second step is to conduct the precipitation process. So this is where you have this chemical equation AA plus RR giving the product of AARR just now. Okay, so this is your precipitation reagent with the blue color. Okay, so when you add the precipitation reagent into your salt solution, it will bind. For example, in this case, the precipitation reagent contains sulfate, which can bind with lead 2+, giving the product solid lead 2+. Solid lead sulfate. Okay, so this solid product is the precipitate or the product of the precipitation process. So from this solid, you can wash it, filter it, dry it, and then weigh it until all the moisture is gone, and you get the mass of the final product, which is PbSO4. Okay, so this is precipitation gravimetric. This is what precipitation gravimetric is all about. You want to take out your analyte from a chemical compound, you turn it into a solution, and then you add in precipitation reagent, and then from there you separate the precipitate produced from the solution through filtration. Okay, all right. Let me unshare this. There are some calculation given in the YouTube video as well. You can watch it later so that you can see how stoichiometric concept is used for solving gravimetric analysis problems. Okay, now we go back to our slide. These are the 7 steps of precipitation gravimetric analysis. The first step is for you to prepare the solution. Just now we have the Pb2 salt. We form the solution of the Pb2 plus salt, right? And then we add the precipitation reagent. This is step 2, the precipitation process. And then the digestion process, excuse me for a while. Because I need to mute participants. All right, we're clear now. Okay, again, I repeat, first step is to prepare the solution. Second step is to conduct the precipitation process using precipitation reagent. And then we do the digestion process. We will talk later, we will discuss later what is the purpose of digestion process. And then we have filtration process, followed by washing, drying and igniting. Sometimes you want to only dry the product to get the final mass of your product. And sometimes you not only require drying, but also igniting in order to get your final product. Okay, that depends on the type of chemical species you are working on. Right, and the last step is the calculation. This is always the 7 sequence of steps that you need to remember when we deal with precipitation process. Okay, precipitation gravimetric analysis. Okay. Okay. Right. The first step, preparation of solution. Preliminary separation may be required to eliminate interfering materials. So you need to adjust the solution condition so as to maintain low solubility of the precipitate and to obtain it in a suitable form for filtration. Okay, so we need to adjust the solution condition so that we can have low solubility of the precipitate and we can filter it. If our precipitate is having high solubility, means it can be dissolved in the solution. It does not form solid, and we will have difficulty when we try to filter them because they are so small in particles. Okay, so what we want is we want to form a large crystal of precipitate so it is in a suitable form for filtration. So what we do is we need to adjust the solution condition so we can have low solubility of the precipitate. Okay, so these are the factors that must be considered. First, the volume of the solution, the concentration range of the solution, temperature, pH of the solution, and presence and concentrations of other constituents. Okay, so presence and concentrations of other constituents means the contaminants or the interference in the solution. Okay. Important conditions of a substance that must be taken into account before conducting precipitation. So this is second step. Second step after you have prepared the solution is to conduct the precipitation process. So remember again, precipitation process is the process of adding precipitation reagent to your solution so they can form the final product, which is solid precipitate. And this precipitate, we want it to be in the form of large crystal so it can be easily filtered. Okay, all right. The precipitate should first be sufficiently insoluble that the amount lost due to solubility will be negligible. This is what we have mentioned just now. We want the precipitate product to be insoluble. We want it to have low solubility because we don't want to lose any amount of our precipitate during the filtration process. Okay, if you go through again, the filtration process is later in the precipitation gravimetry. So we need to make sure that our precipitate is sufficiently insoluble. So it's easy to filter. Okay, it should consist of large crystals that can be easily filtered. It should be stable under atmospheric conditions. When you do say that, when you already form your precipitate, it doesn't change to another compound or another phase. For example, from solid phase, it changed to liquid phase. We want it to be stable under atmospheric condition as a solid precipitate. Okay, and after drying and ignition, known chemical composition should be yield. Okay, we need to say that at the end of precipitation, gravimetric analysis, we want to gain knowledge or information on the known chemical composition and the mass of this compound. This is important to have an accurate calculation. Okay? Then all precipitates tend to carry some of other constituents of the solution with them, meaning to say that when we do precipitation process, if it is not done carefully, we will get some kind of contamination or co-precipitation during the process. Okay? This contamination should be negligible. It should be at the lowest level as possible. Keeping the large crystals can minimize the contamination. Okay, that's why we want our final product to have large crystals, not only because we want it to be easily filtered, but we want to also minimize contamination. As we know, if we have large crystals, we are going to have very small surface area per volume compared to if we have smaller particles, we will have higher surface area per volume ratio. Okay, so if we have higher surface area per volume, meaning that the contamination will be easier to enter the product. Okay, so we want to keep the crystals as large as possible to minimize this contamination. Okay. We know just now that when we conduct precipitation process, we need precipitation agent. So precipitation requires addition of a precipitating agent solution to the sample solution. So the precipitating agent should react either specifically or selectively. What is a selective reagent? Selective reagent reacts with a limited number of species. For example, this precipitating reagent, silver nitrate, can precipitate chloride, bromide, iodide, and cyanide. Whereas, when we talk about specific reagent, it only reacts with a single chemical species. For example, DMG, it only precipitates nickel 2+, no other species. So there are times when we need specific reagent and there are times when we need selective reagent, but all the time we need either one. Okay? The precipitating agent solution is a selective reagent or specific reagent. It's important. All right. After adding precipitating agent, precipitation occurs in steps, okay, in series, meaning to say that it's not happening all at once. Once you add the precipitating reagent, it doesn't happen at the same time. It happens in series, or what we call it step by step. Okay. Now we are going to deal with two important terms. One, supersaturation. Second, nucleation and particle growth. So supersaturation is the condition where the solution phase contains more of the dissolved salts than occur at equilibrium. We will look on the explanation after this. And nucleation and particle growth shows the minimum number of particles that must come together to produce microscopic nuclei of the solid phase. So the higher the degree of supersaturation, the greater rate of nucleation. So now we go more details on nucleation and particle growth. Precipitates formed by nucleation and particle growth. When we do precipitation process, there are two things that will happen to the solution. First thing that could happen is nucleation. The second thing that could happen is particle growth. Okay, and sometimes they happen at the same time. Okay, what is nucleation? Nucleation is a small number of particles in the form of ions, atoms, or molecules in solution which come together randomly and form small aggregates. It can be spontaneous or induced. Spontaneous means they come together spontaneously, but induced means you have to add something in order to make them come together. Come together means they bind with each other. Okay, so you have many small particles. Some of them are ions, some of them are atoms, some of them are molecules. They bind together, form small aggregates. This is called nucleation process. Another process which can happen when precipitation process is conducted is the particle growth. Particle growth is the three-dimensional addition of more particles to the nucleus to form a larger crystal. Let's say you already have one nuclei here. Let's say you already have one nuclei and other ions, atoms, molecules, they come together and bind with this, forming a larger crystal like this. This is what we call particle growth. The particle is growing. Okay. Which one do we want? Nucleation or particle growth? In the previous slides, we were talking about so much about we want the precipitates to contain a large crystal. So which one do we want more? We want the particle growth. Okay. We often find that there is a limit to the quantity of solute which will dissolve in a given quantity of solvent. So from here, I will explain the supersaturated versus the saturated solution. This concept is important because supersaturation is directly involved in the precipitation process. Okay, I'll show you later on. But now I would like to give examples on saturated solution and supersaturated solution. Okay, in saturated solution, let's say you have 36 gram of KCl crystal shaken with 100 gram water at room temperature. Only 35.5 gram of the solids will dissolve in the solution, meaning to say that the solubility of KCl crystal in water is 35.5 gram per 100 gram water. What happened to another 0.5 gram of crystal? Now, if we raise the temperature of the solution, all the KCl crystal will dissolve. Okay, all the 36 gram KCl crystal will dissolve if we raise the temperature of the solution. However, when we start cooling it to room temperature again, the extra 0.5 gram KCl just now, it will precipitate, leaving exactly only 35.5 gram of the salt dissolved in solution in water. Okay, so if we find this situation, the solution is called having a saturated condition. Okay, I give you one example, one easy or simple example. When we want to make a large amount of drinks, for example, we want to make syrup, cordial, okay, and we prepare sugar solution. Let's say we have 1 liter of water and we have 10 kilograms of sugar. So we try to add in all the sugar into 1 liter of water and we want to make as saturated sugar solution as possible. Okay, because we want the sugar solution to be very concentrated. But at the end of the process, we can get only so much. of sugar dissolved in the solution. The rest of the sugar will remain as a solid. They can no longer be soluble in the water, even though we heat it. Okay, so this condition is called saturated solution. So now what is supersaturated solution? Under some circumstances, it is possible to prepare a solution which contains more solute than a saturated solution. It is already saturated, but you can actually add more solute to be soluble into the solution. This happens to some compounds, okay, some chemical compounds. For example, we have sodium thiosulfate, which solubility at 25 degrees Celsius is 50 gram sodium thiosulfate per 100 gram of water. So we know that for every 100 gram of water, the solubility is 50 gram. Now, what happens if we add 70 gram sodium thiosulfate crystal in 100 gram of hot water? And the solution is then cooled to room temperature. The extra 20 gram of sodium thiosulfate usually does not precipitate. It can be dissolved in the solution. So such a solution is said to be supersaturated. It can take more than the amount of solubility at room temperature. Okay? All right. So this is the relationship between the degree of supersaturation and the rate of nucleation. So if we have higher degree of supersaturation, we have higher rate of nucleation. Now, which one do we want? We want nucleation or we want growth rate? Growth rate here means particle growth. Which one do we want to be higher? Of course, we want the rate of particle growth to be higher than the rate of nucleation. Okay, because if rate of nucleation is lower compared to the rate of particle growth, we will have precipitates with big particle or crystals, which is easy to filter and having less impurities. Okay, so this is why we need our supersaturation concept to be understood well. Okay, let's say now we move to the relative supersaturation equation. So what is relative supersaturation? Relative supersaturation, or RSS, is defined as Q minus S divided by S, where Q is the concentration of the mixed reagent just before precipitation occurs. Okay, remember just now, when you have a solution and you add in the reagent, precipitation reagent, and I mentioned just now, precipitation doesn't happen all at once, all at the same time. Rather, it happens step by step. So we can actually determine Q, which is the concentration of the mixed reagent before precipitation occurs. Okay, and S is the solubility of the precipitate at equilibrium. Okay. Now, RSS can be used to estimate or control the type of precipitate that is formed. We want particle growth, so we need to make the RSS as small as possible. Okay, we want the RSS to be as small as possible so we can have more particle growth instead of nucleation. Okay, nucleation, remember, it's a small particles. Sorry, it's a small aggregate of particles, and particle growth means a 3D particles which is attached to the nucleus, and it has larger size compared to the nuclei. Okay, so if RSS is high, many small crystals will form Okay, if RSS is small, we will form larger crystal. Therefore, we want to keep Q low and S high during precipitation. Okay, how do we keep Q low and S high? So these are the 4 important factors during precipitation gravimetry analysis. Okay, during the precipitation process, these are the 4 most important process or factors, because we want to make sure that we keep the Q low and the S high, and we keep the RSS therefore low, so that we can get more particle growth. When we have more particle growth, we have precipitates with larger crystals, which is easy to be filtered and has less impurities. Okay, so we keep Q low by doing precipitate from a dilute solution. Okay, using dilute solution is better than the concentrated solution. Okay, and then we want to add dilute precipitating reagents very slowly with stirring. So what does that mean? We want to make sure that the reaction between the precipitating reagent and the solution to happen perfectly. Okay, so more ions can bind together and form larger crystal. We keep S high by precipitating from hot solution. Okay, make sure that you precipitate from hot solution so that there are more movement of particles, and it enhances the reaction between the precipitation reagent and the analyte. Okay, so precipitate at as low pH as possible is another way to keep the S high. So remember and take note of these 4 favorable conditions for precipitation, because it affects the type of particles that we have in the precipitates. Okay. The first step just now is to prepare the solution. You have your solid sample, you turn it into solution. So that is step 1, preparation of your solution. And step 2 is you add in precipitating reagent into your solution. So it's called the precipitation process. Okay, the process of producing the precipitate. After you have produced the precipitate, the step 3 is digestion. In quantitative analysis, digestion refers to the coagulation of a precipitate into a filterable form, meaning to say that the colloidal particles in the solution, okay, they lump together, they congregate together to form larger particles. Remember, we want the end product, the end precipitate, to have a larger particle. So digestion process is a process that we do in order to initiate coagulation of our precipitate into a filterable form. If you remember the diagram that we showed just now about the precipitation process, you have it in a solution, but it's in the form of colloidal particles. Colloidal particles are small particles in solution which cannot go down through sedimentation and also cannot be filtered because they are so small. They will pass through the filter paper. So what we want to do is we want these colloidal particles to lump together into larger particles by distracting the charges of the particles. Okay? So in this step of digestion, this is what we do. For example, we have silver nitrate solution. We add sodium chloride as the precipitating reagent to produce silver chloride solid as the precipitate. However, The silver chloride solid tends to form colloidal precipitates. Colloidal precipitates means they are precipitates, but most of them are suspended in the solution. They cannot be filtered unless you put them together, you lump them together to form larger particles. Okay. A bit details on colloids. There are two types of colloids, hydrophilic colloids and hydrophobic colloids. Hydrophilic colloids has strong affinity for water. We call it gel. And hydrophobic colloid has very little attraction for water, and we call it sol. Okay, the hydrophilic colloid, we call it gel. Hydrophobic colloid, sol. Okay, this is only some description on colloids. But the most important thing that you should know is colloids are small particles which suspend in the solution. They cannot be filtered because of their small size, and also they cannot make a sediment because they are so small particles that they tend to suspend in the solution. So what we do digestion process. Okay, what digestion process is? Digestion process is the process of coagulation of colloids. There are two common approaches for causing a colloid to coagulate. Number one, heating, and number two, adding electrolyte to the solution. So when we heat the colloid while stirring, we are actually giving energy to the particles to move during the stirring process. Okay, so during heating of the colloid, this significantly decreases the number of adsorbed ions per particles. So it reduces the size of the primary adsorption layer, making it easier for the particles to approach each other. Okay, for now, you can jot down the term primary adsorption layer. I want you to search for the definition of this term. Okay, we're going to take a look at the diagram later, but first jot down the primary adsorption layer. All right, and when you increase the concentration of the ions responsible for the counter layer in the solution, okay, you do like this. You use an unrelated, non-interfacing ionic compound. You add them into the solution. This will reduce the volume of solution that contains ions of opposite charge, which can neutralize the particles. Okay? When the particles is neutralized, they decrease the thickness of the counter layer. Counter layer is the outer layer of your precipitate. The result is that a smaller structure is formed. So after successful digestion, some of the primary electric layer must be washed away for quantitative results to be achieved. Okay. After digestion step, we have step 4, which is filtration. Filtration is passing through your solution through a filter paper or filtering crucible so that anything retained on the filter paper is something that you can dry and weigh later. Okay, so precipitate is separated by filtration using either filter paper or a filtering crucible. So the most common medium is cellulose-based filter paper, and it can be classified according to its filtering speed, its size, and the ash content on ignition. Why size? Because if you have different chemical compounds, they may form different size of precipitates. So you are going to choose the size of filter paper based on the need of your experiment. Okay. When we talk about filtration, even though we filter our precipitate, it during precipitation, the precipitates tend to carry down from the solution other constituents, which is normally soluble, causing contamination to the precipitate. Okay, so this process of contamination of the precipitates is normally known as co-precipitation. Co-precipitation means you have your precipitate, but not only the precipitate, it comes together with contamination. Okay, so we call it co-precipitation. Some of the sources of co-precipitation including the occlusion, inclusion, surface adsorption, post-precipitation, and mixed crystal formation. Okay, what I want you to do is for you to self-study these sources of co-precipitation, and in the forum later today, okay, we have another 2 hours of this class today. You can use the time to study what this means. We have the notes on this, but you have to study more. Okay, occlusion, inclusion, surface adsorption. You choose 2 of the source of co-precipitation, and you comment and share information in the forum. Okay, in eLib, of course. So these are some short description on what is inclusion, what is occlusion, and other types of co-precipitation. Okay, so this is a diagram showing counter ion. Counter layer is the outer layer of the precipitate. Okay, this is might be the adsorbed impurity for surface adsorption. Okay. Okay. Now we go to step 5, which is washing. After filtration, it's crucial to wash the precipitate very well in order to remove all adsorbed species, which will add to the weight of precipitate. Okay, after you filter, you do washing. Some of the primary electrode layer must be washed away for quantitative results to be obtained. Because if you don't wash it, you are going to dry and weigh your precipitate together with the contamination or washing, other agent. Okay, so what we want to do is we want to remove the counter layer, primary adsorptive layer, okay, and we want to make sure that the precipitate remains as a big, large crystals so that it can be easily filtered. Okay. All right. In this case, we have an example of silver chloride colloidal particles and adsorptive layers when Cl is in excess. Let's say we have, in this case, silver chloride. Chloride absorbs on the particles when in excess. Okay. A counter layer forms. The neutral double layers causes colloidal particles to coagulate. Okay, so the neutral double layers, they cause all the colloidal silver chloride to coagulate. Remember previously or earlier we mentioned that, let's say we have silver nitrate bind we have silver nitrate and we have sodium chloride as precipitating agent. It will yield the product of silver chloride, and silver chloride is normally in colloidal form, but if we do digestion process, it will go into this form, which is large particles form, okay, where all the small particles coagulated during the digestion process, and then we filter it, and then during washing process, if you wash this with water, you could dilute the counter layer and the primary layer charges, which causes particles to revert to the colloidal state. So from here, we know that in the case of silver chloride, we don't want to wash it with water. We don't want to do the washing with water, because when we wash it with water, we are going to induce peptidization. We are going to break the coagulated particles into colloidal state. Mean to say that we undo what we did during the digestion process. We don't want that to happen. Okay, so what we do is we don't use water, but we can use a volatile electrolyte. Washing with a solution of a volatile electrolyte helps to prevent peptidization. Okay, and after you wash with the volatile electrolyte, you heat the precipitate so that you can remove the volatile electrolyte. For example, in the case of silver chloride, if you wash with HCl, you dry the precipitate at 110 degrees Celsius, you will remove HCl from the precipitate. So it's easier. Okay. The conclusion here is when you wash with any washing agent, you have to consider whether the washing agent that you use will cause peptidization or it will have no effects on the coagulated precipitates. Of course, we want the final product to be large crystal, so we want to keep the coagulated particles or precipitate. We don't want the peptidization, because the peptidization will cause the coagulated particles or precipitates to form smaller colloidal particles. Okay, so this is the comparison between peptidization and coagulation process for you to understand more. You can read it on. Now we move to step 6, which is drying and ignition. The purpose of drying is heating at about 100 to 150 degrees Celsius in an oven. So the purpose of drying is to remove moisture, and the purpose of ignition is to remove volatile matter from the sample. Okay, and sometimes ignition is used to change the chemical formula or the chemical structure of a compound. Okay, why we want to do that? Because sometimes it helps the calculation of or the determination of your analyte if you change it into a different type of compound. Okay, we'll see some examples later. The purpose of drying and ignition is to get a material with exactly known chemical structure so that the amount of analyte can be accurately determined. Remember, the precipitates must be in suitable form of weighing. Many precipitates contain varying amounts of water and adsorb electrolyte from the wash liquid. So when we heat it at 110 to 120 degrees for 1 or 2 hours, we will remove those moisture and adsorb electrolytes. Okay, so we dry the precipitates for accurate and stable mass measurement, and sometimes we need ignition to convert the precipitate to a more suitable form of weighing. All right. The temperature required to produce a suitable weighing form varies from precipitate to another precipitate. Okay, so if you have different compound, it has different behavior towards heating, drying, and ignition. Let's say we have silver chloride. If you heat it or dry it at 110 to 120 degrees Celsius, it doesn't matter if you increase the temperature up to 1000 degrees Celsius, it still become silver chloride. It doesn't change to any other compound. Okay, at low temperature it is silver chloride. At high temperature it is also silver chloride. But different characteristic or different situation happens to this compound, aluminum oxide. Here, at a very low drying temperature, 110 to 120 degrees Celsius. It has water bind to it. You only remove the outer moisture but not chemically bind water. But if you heat it up to 1000 degrees Celsius, you have a pure compound. So the pure compound is more suitable form to be weighed and calculated. Okay. Let's see another compound here. So at different temperature, it is a different chemical structure and different chemical formula. So 110 different, 500 degrees Celsius different, 1000 degrees Celsius different. So sometimes we need this compound for calculation, sometimes we need this compound for calculation, and sometimes we need this compound for calculation. Okay. So at different temperature, you yield different compound, and the calculation and the information that you have for calculation could be different. So now this the last step, which is the calculation step. So all calculations dealing with gravimetric analysis are based on stoichiometry calculation. So you need to establish the mass relationship between the analyte and the sample actually weighed. So normally you have to do balance chemical equation and determine the moles, and from there you determine the mass of any species and so on. So these are the things that we are going to cover in our next lecture. So remember, today you have learned two things. First, three things actually. First, you have learned the concept of gravimetric analysis, the type of gravimetric analysis. You have also learned the 7 steps in precipitation gravimetric analysis. Okay, so in our next lecture, we are going to cover the calculation, some of the calculation examples for gravimetric analysis, and we're going to cover a bit on the volatilization gravimetry and particulate gravimetry. Okay, so if you haven't scanned your attendance yet, you can leave your metric number in the chat box, and if you have any question, you can always ask in the group, the chat group, and also you can email me. So with that, I hope you can use another remaining 2 hours of today to complete the activities on ELIP. Thank you very much for having me for 1 hour, and I hope you can complete the ELIP activity. Thank you very much. See you again next week, inshallah.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank